In this video, we will be looking at simple linear regression. That is, finding a linear relationship between one dependent variable y and one independent variable x. A simple linear regression can be expressed in this form: y equals beta 0 plus beta 1 times x plus the error term. Here, beta 0 is the intercept of the equation, where the line crosses the y-axis. Beta 1 is the slope of the equation, as it is multiplied by the independent variable. The last term, the error term, comes with some assumptions. First, we say that the error is a normally distributed random variable that has an expected value of 0 with constant variance. We'll come back to these assumptions a little bit later on and how to check their validity. But without these, if these assumptions do not hold, then your linear model is not valid. So the goodness of fit of a linear relationship is measured by the correlation coefficient rho, and this is approximated by R. And it measures the degree of linear relationships between variables, and it's always between -1 and +1, where the closer the absolute value is to 1 of R, the stronger the linear relationship. 0 means there's absolutely no correlation whatsoever, and no relationship. And the value of R is independent of which predictor, the value of R is independent of which variable is the response and which is the predictor variable. And it's also independent of units of measurement, which makes it a really good comparison between models. And if you square this value, you get the coefficient of determination, R squared. And so that's the percentage of variance in the dependent variable that the linear model can explain using the independent variables. And this is also another good measure of how well your linear model is fit to the data. We can also perform an analysis of variance, or ANOVA, on the simple linear regression model. What this does is it looks at the breakdown of variance again in the model and performs an F-test, or calculates an F statistic for a hypothesis test here, where your null hypothesis would be that there is no relationship between the independent and dependent variables, and your alternate hypothesis would be that there is some relationship. So let's look at an example in R. Here you can see I've already typed the data into R. We have one x variable and one y variable, and right now these are just in vectors. But to make things a little bit easier on ourselves, we'll put them into a data frame that we'll call our linear data. And this just uses the data frame command and puts two vectors together. So now you can see we've created a data set. It's under data instead of values, and it has 14 observations of 2 variables each. We'd also like to put names to that data using the names function. And we'll say that the first one is the predictor, x, and the second one is the response, y. Okay, so now if we look at the linear data in R, we can see our data up here with names. So first let's plot the data to see should there be some sort of, is it a valid assumption to think that maybe there's a linear relationship here? Linear data. Now we can see from this graph over here that there does appear to be some linear relationship here. Not perfect, but there is a trend there for sure. So now we'll fit a linear model using, we'll call our model fit, and we'll use the lm command for linear model. And what this takes a few different arguments. First, you specify your response variable, which in this case we named response y, and then note that's a tilde and not a hyphen, to your independent variables, or your predictor, x, and then you have to tell it where to look for the data. So the name of our data set was the linear data. Okay, and again this puts our value right up here, which we can call a summary of using the summary command. Okay, so this shows us our linear model. And the most important part of this, arguably, are the coefficients, telling us what the actual model is. So our intercept is negative 3.555, and our slope is 1.46. And you'll also note that there are significant codes down here, and this just tells you at what level of significance are all these variables important. So you'll note that the slope, or the predictor variable, has 3 stars, which indicates that it is significant at a level of 0.001, which is highly significant. It'll also tell us the r squared value and the adjusted r squared, which are both 0.96. So that's a good indication that there is a strong linear relationship here, and that we've explained 96% of the variance in the dependent variable just using one independent variable. So now we're going to try and check those assumptions that we talked about before in terms of the error. And we do this using the residuals, because the residuals are what the difference between the actual values here and the line, the linear model that goes through them. So those will result in the error terms. So first, we're going to say that we want to look at 2 plots at one time. So we'll split this plot area into 2 using this command, just a handy little one-liner to keep in your back pocket. If you don't forget to put a C there. There we go. And so now we'll look at the QQ norm plot of the residuals of our model called fit. So this plot tells us if our error terms or our residuals are normally distributed. And if they are, this should be these points should form a perfectly straight line at 45 degrees. And we can also, if it's easier, we can also plot a QQ line of the same thing over that. And you can see that they kind of follow that trend, but not really. There's especially some deviation down here, which indicates that they may not be completely normal. So that's something to, keep in mind. But next we'll plot the actual residuals against the fitted model. Okay, so we'll look at these a little bit bigger. And we can see that, well, when we blow this up, that is better fit. It's a little bit closer to normal. It's not perfect. We also don't have a huge data set. It's only 14 data records, so it may be a function more of the sample size than the normality of the errors. Looking at the fitted values of the function versus the residuals, here what we're looking for is the spread. So we can see that they do look randomly distributed. There's no real trend here, and the variance does look to be constant. So we can say that our assumptions fit pretty well. And lastly, we can perform an ANOVA analysis, which is just using the ANOVA command and your linear model. And what that will do is print out an ANOVA table. And what you are looking at here is the p-value here, telling you, is this significant? Again, for an analysis of variance, your null hypothesis is that there is no relationship between the independent and dependent variable. And your alternate hypothesis is that there is some relationship. So you can see here that this is, again, highly significant, which indicates to us that we reject the null hypothesis and we say there is some linear relationship here, as we would expect from looking at both our residual plots and our adjusted R-squared value. So more information on simple linear regression and ANOVA analyses can be found in your textbook, Probability and Statistics for Engineering and the Sciences, the 8th edition, by J. Devore.